looking actually courses where some either part of the course or modules or full course, all the options are available. So the courses should be jointly taught by jointly taught by our faculty and the industry people. That is a kind of model, or full course taught by the industry people, depending upon their availability.
Sure.
So the option is also either they can once a few slots they can visit the campus and they can finish. Okay, let us say in the span of 4 months of a semester, in the weekends or sometime you arrange some. They come and one day some certain modules are finished like that, or online modules. So we are looking at all. Actually, we are keeping. We want to have the industry exposure to our students. So that's the gap in the skills would be bridged. Okay, we are looking at that kind of model. So we are open for, actually we are quite flexible and open. So there is no rigid any structure or anything. So that is one advantage of our university actually.
Okay. So yeah, so I mean, we can work on something. I mean, I will probably have a bigger discussion regarding
definitely we can have a separate discussion
and all, right? Because it should also be something that is in my expertise area. I shouldn't be talking about things that are, and it should be relevant to the course and the students, right? So what departments use? I think Manoj
EC, electronics and communication.
EC, and there is also IoT. There are two departments.
Yeah, IoT is MTech in IoT actually. We have MTech in IoT. It is also from the EC department.
Okay.
So we are in EC department. We have BTech in EC as well as 2 MTech courses presently we are providing. One is MTech in IoT, another is MTech in VLSI.
Okay. And what are all the departments that are there currently?
Currently, besides computer science, we have mechanical engineering, we have EEE, that is electrical engineering, civil also there.
And EC.
EC. This is from engineering side. And from science side, we have physics, chemistry, biological science. Some economics department is also there, and some humanities department like English, history, they're there.
So this is basically functioning as a university.
Yes.
Right.
It started as a research university.
So we have other senior faculty members from the department, Professor Gigi, Professor Shivshankar. Okay. So they joined in the attendees. So they also some senior faculty members are there in the attendees here.
Who this is the second lecture in the series, right? Who presented in the first one?
It is Dr. Sirin Banerjee.
Oh, okay. She's my batchmate.
Yeah.
I know her pretty well. I actually last weekend I was traveling from Calcutta, so I met her in there. She was also traveling, so I just
she was also there that time in Kharagpur actually.
Yeah. So I suddenly bumped into her in the airport. Yeah. Good. Hi, Dr. Indranil.
Hello, sir.
So this campus, what's the closest airport? Vijayawada, is it?
Vijayawada,
yes.
From Vijayawada, it looks on the map. It looks reasonably close. Maybe what, half an hour, 1 hour?
1 hour. Yeah, depending on the traffic, 1 hour journey. So.
Somebody. I will just check if the sharing is working fine.
Good morning, Professor Gigi.
Good morning, Dr. Ramesh.
Yeah.
Good morning. Good morning, Dr. Amit.
Hey, good morning.
Yeah, good morning. Actually, I am also working in the field of computer vision.
Oh, nice.
Yeah.
I am just trying to enable sharing because it might. Let me see.
Shall I start the event?
Just a second before. I want to just make sure that the sharing is working fine. Okay, so.
Manoj, it's for faculty members only, or students are also joined?
No, sir. Students even outside also no problem. Anyone can join.
Okay.
some problem that I'm seeing. I am unable to share my screen for whatever reason. Allow Zoom to share your screen. Allow the apps below. Okay, maybe I need to add. So. I might have to quit Zoom and reconnect. Okay, so. Okay. Start video. Let me just try and share again. Yeah, now it should work. Okay, I am ready. So whenever you are.
Okay.
You can see this my screen, right?
Yes, we can see it. Okay, just give me one more time. Good morning, everyone. I welcome all of you to the EC Department Distinguished Industry Academy Interaction Lecture Series 2. The talk will be delivered by Dr. Amit Kumar Shah. The title of the talk is Computer Vision at the Edge. I also welcome to the other panel members in this talk, our HOD, Dr. Ramesh Morvadi, Professor GGCB, Professor R. Ramakrishnan, Dr. Indranil Hatai, and other faculty members. And as well as I also welcome all the participants. In his short biography of Dr. Amit Kumar Shah, he is presently a principal engineer at Cisco Meraki, Bangalore. He has received his PhD degree from Rice University in 2007. Prior to that, he has obtained his BTech degree from IIT Kharagpur with recipient of Dr. B.C. Roy Gold Medal in 1999 from the same institute, to a single graduating student with the best mix of academics and extracurricular activities. Dr. Amit explores the next generation of technology at the intersection of networks, distributed systems, and data sciences, with a special emphasis on system-wide design. He is part of Cisco Meraki's camera intelligence team and enables Cisco's internal products as well as customers better manage their AI/ML life cycles by making it easier to train and tune models and deploy distributed machine learning workloads. He passionately seeks out opportunities to give back to the community through talks, research, collaboration, organizing conferences, and as a visiting faculty at several top institutes in India. I request Dr. Amit Kumar Shah to deliver the second EC DDIAIL lecture.
Thank you, Dr. Manoj, and I would like to thank the department for this wonderful opportunity. It's a great honor to be presenting to the department, the students, and probably some other attendees from outside the university as well. So as already mentioned, the talk is titled Computer Vision at the Edge, right? And I am going to talk about my experience in at Cisco Meraki, where I am working in the camera team. So the team is called Camera Intelligence Team. We are working on developing multiple machine learning models that are installed on our cameras, and that allows us to do certain kind of inferences on the camera. So I will go through the talk. The talk should be over around, say, maybe around 45 minutes or so, leaving us some time. I mean, we have 1.5 hours, but I don't want the talk to go all the way to 1 hour. So I'll try to wrap up by 45 minutes, maybe a little bit here and there. As far as questions are concerned, I suppose Dr. Manoj or somebody might be, because I can't see any chat messages here. So if there are questions, please feel free to interrupt me whenever you think it is that I am reaching a particular. I will also ask if there are questions till now. In case there are no questions, I'll keep moving, and I will also look at it at the end. We can also take all the questions at the end. That's fine. So whatever works. We shouldn't be pressed for time in today's talk. So again, the title is Computer Vision at the Edge. So let me start with a discussion about a forecast of IoT connections in the world, right? So this is a report from Cisco itself, and the report says this was done pre-pandemic, so there might be slight changes or a downward trend in these numbers, but still the numbers are huge, right? So it says here that by 2023 we are around 14 billion IoT connections, right? Which is roughly, I mean, with a world population of around 7 billion, we are roughly at 2 connections per person by 2023, right? This is obviously a staggering number of connections that we have never seen in the history of our world. These many devices being connected to the network, right? Now, this obviously brings in a lot of challenges, and we'll go over specific challenges, and in the case of computer vision, what those challenges are, right? Now, what is kind of the split of this IoT industry, right? Again, this is again from the same report, the Cisco. This report is available publicly. So if you search for, I think Cisco IoT report or something, you should be able to get it from Google itself. Now, if you look at it, there is, again, let's look at 2023. The biggest chunk is this blue piece, which is connected home, right? And the growth rate of it is also huge. It's a 20% growth rate, right? And then after that comes this, which is the connected work piece, this dark blue one. And after that, there are other pieces which are relatively small, even though there is energy sector. Then there are connected cities, which is this gray part, which we hear a lot about the government smart city plans and all. This falls in here. And then connected cars is another big chunk, which is growing very fast. It's a 30% growth rate, right? But anyway, these are relatively small compared to the others. And we can see that almost everybody has multiple mobile devices at home. There are multiple devices which connect to the network. All smart TVs are now connected to the internet. It's very difficult to not buy a smart TV these days. If you go and want to buy a TV, it's going to be a smart TV. So it would require a connection, right? So other than that, so this is kind of the breakup of the industry, right? So huge connections. Also in the connected home scenario, there are your Alexas and your Google devices, all these voice control devices, a lot of different stuff, right? Even refrigerators are coming. We see ads of geysers having internet connection so that it connects to the Wi-Fi and you can automatically control it. Washing machines are connected to the internet. Everything is getting connected. Everything that has a chip, it's very easy to now add a module which will have an internet connectivity. And practically every instrument that we use has a chip. Now, what are the types of devices? Again, in this market, this is again something expected. There are 2 major blocks here. One is the smartphone block, which we can all understand. So this is the blue block. This is primarily the biggest block. Currently, it is still the biggest block. It is expected that this might not be the same after some years. And the other mobile-to-mobile communication, which is basically, machine-to-machine communication, which is basically devices communicating to devices, is catching up, and it is very soon going to be maybe it'll very soon take over mobile smartphone communications, right? Because as you see, most devices these days are communicating with another devices. For example, in India, almost the entire electricity supply or the connections at the home, the meters are becoming smart meters, so that they can directly communicate with another device and report your usage and things like that. There is a lot of car-based communication, which are again machine-to-machine communication, right? So these are all the things that are driving the IoT revolution, if you want to call it so, right? The IoT revolution is not new. We have been studying sensor networks for at least the last 20-25 years. And sensor networks was, when I was doing my PhD, sensor networks was among the very hotly researched topics. A lot of theses came out, at least in the Western world, on sensor networks. There's still research on sensor networks, but sensor networks are basically IoT devices. But with the proliferation of the 4G network and then the 5G and now the upcoming 6G networks, the capability of the network to support millions and millions of connections is now a reality. And so the IoT systems are also becoming practical to build because the network is available. And all industries are going towards automation, things like that. So IoT as such is going to be big, right? It is already big, but it's going to just keep on increasing. Now, what is actually allowing this sudden growth in IoT devices, right? I just wanted to give an overview. There is an URL on the heading of the slide. By the way, I will share this slide to Dr. Manoj, and he can probably share it with others. So you don't have to take notes here. So these are basically embedded platforms that are available from ARM, right? So these are all ARM-based platforms. Now, these are too small to see. You can go to this URL and see. But basically, a lot of different devices. These are just ready. You can go and click, just like in Amazon, click and buy them. This will come to your house. Obviously, I mean, being in India, not all of them will be available, but you can buy them, and some of them has some different kind of sensors. This has ARM Cortex microcontrollers or ARM processors, all these kind of things are already fitted into this. This has connectivity to like serial ports and stuff like that. And so you can build an IoT device, as in at least a prototype of an IoT device sitting at your home. You don't need much. These things are all available. Earlier, just building one of these would need like a dedicated hardware team, board designers, and all those people who would actually have to build this for you, right? Now, if you want to build a humidity sensor, you can basically get one of these boards, plug in a humidity sensor, and you are done, right? It's very easy. So this has led to tons and tons of companies which are building IoT devices, and that has led to the increase in the IoT devices, including large-scale companies which are making appliances such as your washing machines, your microwaves, your geysers, your cooking stoves and ovens and whatnot, right? Every device is now trying to have internet connection. So, as I said, the IoT space is not new. IoT has existed for a long, long time, at least for the last 20 years. And during that time, there has also been another big change in how we manage our computation, or where we do our computation, is that we have slowly moved from on-premise server farms and all to the cloud, right? So because the cloud in principle allows us infinite elasticity, so infinite resources. We never really have to worry about scaling up our servers or our connections or our storage, anything of the sort, right? So it provides us with elastic computation, elastic storage, and elastic network, right? Now, so that movement also happened in the last maybe 20 years, 25 years, again, towards the end of the last century and towards the start of the first decade of the century is when people started moving towards the cloud. Even now, a lot of stuff is legacy and runs in local server farms or inside the premises, but a lot of companies are moving towards cloud. A lot have already moved towards cloud, and a lot of companies are moving towards cloud. And what has happened with the existence of these public clouds like your Google Cloud or your Amazon AWS Cloud, or Microsoft Azure Cloud, is that you and me can now suddenly think of, hey, I want to design, say for example, you want to design a heat monitoring or temperature monitoring system for your campus, right? It is now possible for you to design and build it within a semester as a course project, because you don't even have to worry about the computation part of it. You just need to worry about the sensor part of it and what you want to do with the data as interesting application. Building the system with the sensors, you can just outright buy the sensors, connect them to the internet, and your cloud takes up the ability to do all the computation, right? And provide you the storage and the network connectivity. So students themselves can do this very easily. So within, I can expect that within a semester, you can offer a course in which people will be able to build, and the focus of the course will not be actually building it, which you would get done in 1 or 2 months, but the focus would be actually in developing intelligent applications on top of it. Right. For example, automated switching of traffic lights, or automated switching of lights in the evening, switching on lights in the evening, switching off in the morning, things like that. Right? So the traditional edge was something like that. You have sensors, and all the data from the sensors is moved on to the cloud. Right. So everything goes from the sensor to the cloud. So the sensor by itself is pretty much dumb, in the sense that it can just read and transmit. It doesn't do any actions. And here it is shown an Azure IoT Hub, but it could be any of the cloud providers or some proprietary solution. That doesn't really matter. So it comes to this cloud gateway, and then in the cloud, you perform computation to get your insights. And finally, you have actions, which are again then sent back to this gateway, and those actions are sent back to the sensors. Right. So for example, if there is a temperature sensor which is controlling, say, the what should I say, the air conditioning system in the building, right, in the department, say, then the sensor is giving the temperature reading, the cloud is making some analysis, and finally that data goes back to a different sensor, which is, or different controller, which is controlling the air conditioner, and can increase the temperature or decrease the temperature of the air conditioner. So this loop is there in the traditional edge architecture. It has to go to the cloud decides and comes back. The sensor by itself is dumb. It just reads and does what it's told to do. This is all well and good, but there is a problem with it, right? What's wrong with tradition? Right? There is I see in the chat that there are some disconnections and all. Am I still audible? Everything is fine from my side?
Yes, you are audible.
Okay.
You are audible.
Sure. So what's wrong with tradition? There are some problems with this traditional approach, right? First of all is the latency. Right? So as the previous picture showed, we take the sensor data, send it to the cloud, process it in the cloud, and then get back the action back to the sensor, right? So this is a round trip type to the cloud. And depending upon how your network is and what kind of service you've bought from the cloud, things can take long, delays might be very high, especially depending on the application. So for example, if it's a fire alarm system and you want the sensor to be very quick, right? The action to be very quick, you can't really be dependent on the cloud. For example, again, as an example, if it's a camera-based system and you want an intrusion detection, like somebody has opened the door in the middle of the night and it was not supposed to be, right? If you send the data video file to the cloud, the processing gets done, comes back. By that time, it might be too late to stop that. Right? Instead, you want something very quick. So latency is a big issue. Data volume has become a bigger problem now because, as I said, billions of sensors are being expected in the world. And that is, even though most sensors send very minimal amount of data, there are sensors like cameras, which are becoming more and more high resolution with each passing day, that use a lot of data bandwidth, right? So if you have to ship all the data to a processing center, which is in the cloud, obviously the network in the middle can become a bottleneck, right? So the amount of data generated in some edge devices is very high, right? And again, here Gartner estimates 25 billion edge devices. I had showed a estimate, Cisco's estimate was around 14 billion. doesn't really matter. It is in tens of billions of devices, right? So the network pressure is likely to be high, even with solutions like 6G, which promises a very high bandwidth compared to current technologies. Right? The third issue is security and privacy, which is something that often as technologists, especially in academia and all, we kind of ignore a little bit, because most of these concerns are from a policy point of view and not from a technology point of view. What I mean by that is that government comes up as policy saying that, hey, you are not allowed to share some kind of data from your local devices to the cloud. Or if you do share it to the cloud, then it has to be in a geographical region. For example, I mean, your Aadhaar database can be in a cloud, but the cloud cannot be physically hosted in any place outside of India, right? Or maybe even within India, there are restrictions, right? Things like that. Those are policy issues. The solutions to it are obviously technical. I mean, there are a lot of security people working on those things, as well as how to manage all these things from an installation and deployment point of view. But these are concerns that usually come up when people voice their concerns. Like, I am not happy that my picture would be sent to a cloud in the US to process and figure out how many people are there in the room, right? I would rather have that stay within my company, right? A company might not be comfortable saying that, hey, there was a fire hazard inside the company, right? It is important for the company to know and to solve it. But if that kind of information goes out saying that, hey, Cisco's office had a fire hazard yesterday and it is happening very frequently, then that could lead to a lot of bad press, right? So people are very worried about those kind of information going to the cloud. Even though the cloud has its own security policy, it is somewhat outside your control. Leaks do happen every day. We hear about credit card leaks and bank transaction frauds and all those things, which presumably have higher security requirement, but even then these things happen, right? So there is a lot of concern in having the data inside the premise. So again, by 2022, which is this year, again, 50%, more than 50% of enterprise generated data is expected to be created and processed outside the cloud, which means on premise of the enterprise where it is being generated. I don't know if this 50% number is true or accurate, but it means that a sizable chunk of the data cannot actually be pushed to the cloud, just from a policy point of view. So now the traditional edge has now moved on to the intelligent edge, right? Again, these diagrams are available on ACM Communications. I took this from ACM Communications. So these are all freely available. And I will share this PowerPoint anyway with you folks. So the intelligent edge is slightly different. You still have a cloud where you can do your heavy lifting, like heavy training with lots and lots of data. You can do your training or machine learning models or what kind of analysis over multiple days or weeks or years. That can still happen in a cloud because the cloud does have access to potentially infinite resources, right? However, on the sensor side as well, you now have basically a similar kind of workflow. The sensor is no longer dumb. It can take its own insights and it can perform its own insights and can take actions on the insights, so that the sensor by itself is self-sufficient to some extent. So for example, the sensor, just as an example, a temperature sensor might have been programmed with some threshold, say 15 degrees and 25 degrees, that if it is below 15 degrees, start the heater. If it is above 25 degrees, start the cooler, things like that. And it is all well and fine, but then such sensors, multiple such sensors might be reporting the data back to the cloud, and the cloud might be doing a processing over, say, an entire year and figure out, hey, our electricity budget is a little bit too high. Why don't we tweak the thresholds a little bit based on the data that we're getting? So most of the time we are seeing that we don't really need it to be 15 or 25. We can make it, say, 18 and 27, something like that, right? That kind of analysis cannot be done by single sensors or even a few sensors together. You need to have a view of large number of sensors as well as the data has to span over a large amount of time in order to make intelligent decisions, right? So this is the intelligent edge model that basically the IoT has moved towards, right? I mean, you can still find the traditional edge model, but the new model is pretty much, this model has also started to take off. Now, I have given an overview of basic IoT as such, and the architecture for the edge, intelligent edge. Now I'm going to now move to the title of my talk is computer vision at the edge. So now I'm going to move towards the video part of IoT, and that is the video surveillance part. And the rest of the talk will focus on the video surveillance and computer vision at the edge. Again, this is not a talk about computer vision algorithms, but this is about how do you manage computer vision at the edge when you have large number of cameras which can run machine learning models, or even maybe not necessarily machine learning models, but even other kind of software, right? Anyway, so this should be these devices should be kind of familiar to everybody. So this is how video surveillance was done in the past. So you would have your cameras, these are cameras, right? And then you would have your own network box. And then you would have this is like a recorder, right? Recorder and a CPU kind of stuff where everything is stored. If you go to many apartment complexes and even maybe university buildings and all, this is probably still present in many places. So the way it works is that everything is a proprietary solution, and you have kind of a monitoring room within your campus where everything comes and the data comes, and you have to have your own network, and the data comes and it is stored in your local computer or storage, and you have a way of viewing it, analyzing it, and whatnot, right? For example, in most cities, police requires you to have video monitoring system in apartment complexes and wherever more than one family lives and things like that, right? So this is quite common. Now there are several issues with it, right? The biggest problem is that it's a huge management issue, right? You need network video recorders. It's a separate device. You need server storage. You have to provide your own network, and on top of it, every company has their own proprietary software. The upgrades of the software is a big problem. Somebody has to come and do a site visit and things like that. If things go bad, managing it is a huge issue. So this is cumbersome and clearly not that easy to scale, which is why these systems are usually quite expensive. Now, video surveillance has come a long way since then, and now the way forward, as a matter of fact, the way it is done in most kind of new age video surveillance companies, including Cisco Meraki cameras, is that these cameras are itself now pretty intelligent. The cameras themselves have on-device storage, and they themselves are basically, the form factor is reduced so much that they themselves are now capable of having an Ethernet connection and everything, or even Wi-Fi connection, right? These come with Wi-Fi connection, and they have a connection to the internet, and you can do all the storage in the cloud, right? And so you can access the video remotely. So once you have put everything in the cloud, you can also do your local video access. Obviously, if the connection to the cloud is even not available, you can do your local video access because this network is still up. And because of the presence of the cloud, you can use the remote video access, and you can use your smartphone app or anything to look at videos or streams and all those kinds of things, right? So it makes the management and the usability much better. Why is the management better? Because now everything is connected. You can do upgrades remotely. You don't need to, unless there is a hardware failure, practically there are no physical visits needed to the sites. These are just not done anymore, right? Also, these devices have on-device storage, as this picture shows. What that allows is that if the network actually goes down, either the network the network meaning its Wi-Fi connection to whatever the gateway is, right? Or its wired connection goes down, or the connection to the cloud where it is being stored goes down. It doesn't matter for a reasonable amount of time, right? So what happens is that it can store within the system itself, within the cameras itself, and when the network comes up, it can it can send this data back. Right? So this is kind of the new model. I mean, this is Meraki's model, but practically every new company which does video surveillance has something similar. Right? So there is on-camera. Okay, one thing I have not spoken about is these cameras also have on-camera intelligence, which means that there are actual models running here which can identify certain things. For example, it can identify how many people are in the room, or it can identify, say, heat maps of staircases, seeing that, okay, are too many people taking the staircase, right? Because that's a fire hazard, or that's a hazard. If somebody trips, then a lot of people can get injured. If too many people are in the parking lot, or things like that, right? So a lot of those models are there, and the models, I will probably not go into that. We have very recently opened up the cameras so that people can install their own models. So somebody might be interested in something very specific. For example, if you install these cameras in your campus in a lab, you might be interested in seeing that, okay, if a particular device is proper or not, if a particular device is at the position where it is supposed to be, if a particular device is in a correct orientation or not. So those are specific models that somebody would have to develop, and it is not our core competency to be able to develop that. Right? So, and these are bandwidth conscious in the sense that if there is nothing to report, if the scene is not changing too much, then the network usage is very low, like 50 kbps or something like that. But if the scene is a lot of action is happening, then you increase the network usage, right? And as I said, cloud for longer retention. Just an example of a few of the cameras that we sell. These are among the few of the cameras. So like this one is one which is very compact form factor. This is actually, when you close this in this form factor, it is the size of a Coke can, right? A soda can. This one is with the 360-degree field of view. This is used in places like maybe ATMs and places where you need to have a large wide angle view to see a lot of things. And then these are outdoor ones where IK10 plus and IP67 are outdoor ratings. So which means that these ratings mean that some sort of waterproofing, as well as if somebody really throws a stone at it, it will still continue to work, things like that. These are needed for outdoor cameras. These are some standardizations, right? So these devices have up to 1 terabyte, not 1 terabyte GB, 1 terabyte of storage on the camera. And as I say, the camera can function without having to store in the cloud, without the network connection. And it uses camera filtering to store intelligently. Example, like store only when there is a change. Like for example, if you're looking at a room, nothing. If you're looking at an ATM, right, nothing is happening. Somebody enters, the door opens. That's when action starts happening, and that's what you store. Right? And again, when the door closes, you stop storing or something like that. So those kind of intelligence is there in these cameras. And it can run, these can run multiple ML models, object detection, motion heat map, and there are dedicated machine learning chips on this cameras. Right? I will not try and play this. Tell me if you can hear the audio of this. If the audio doesn't play, then I will stop playing this. Is the audio, can you hear the audio?
No, we cannot hear the audio.
Okay. So then I will skip it. It's nothing. It's basically, once I share this slide, you can look through it. It's basically a use case where a partner of ours uses Meraki cameras to do certain interesting things. Anyway, so I will skip this. Okay. Now, what are making these kind of cameras possible, right? Why were earlier cameras kind of dumb and these cameras are becoming smarter? Right? Because now you can, again, just like the ARM-based IoT boards that I was showing you, there are now these boards known as edge processing units. I mean, it's not a very commonly used term, but I kind of used it here, is edge processing units that are available. So for example, the Coral Edge tensor processing unit, this is from Google. Then there is NVIDIA Jetson Nano. This is from NVIDIA, of course. Now look at these specifications, right? At 2 watts, this Coral can do 4 tera ops per second, right? tera operations per second. And it can do like a MobileNet V2 object detection model at 400 frames per second. Right? So this is a pretty capable device, and look at the size of it. Like it will, two of them will easily fit in your palm. Similar to the NVIDIA Jetson, it has 471 gigaflops. So they do their measurements in floating point operations at 5 watt. Right? This was at 2 watt. This is at 5 watt. Right? And here it is tensor operations, which is slightly different than floating point. Floating point is much more complicated operation. So that's why the numbers are lower and the power usage is higher. But then you can see that 2 watt, 5 watt, you are getting so much operation. And it has a 128 core GPU inside it. These are all small devices. You can now fit them into compact form factors, and that is what is allowing the devices like this to come up in the market. Earlier, these were simply not possible. So now we have all these devices in the, we have all these camera devices. Now, these obviously lead to some challenges. So these are the challenges now that I'm going to focus on. So these are kind of also indications of possible research areas where both faculty and students can look at. And these will continue to be challenging areas for at least the next 5 to 10 years, because we are barely scratching the tip of the iceberg when we are talking about the IoT world. Right? So first of all is the network impact. Right? So I've shown this picture earlier. Everything is trying to go to the cloud, right? There are a huge number of cameras and everybody is trying to store stuff in the cloud. Of course, they can handle some sort of network outage, but not for too long, because the on-device storage is going to run out. So this puts considerable pressure on the cloud, even though things are bandwidth conscious, right? Because bandwidth conscious, you can only be bandwidth conscious when you're seen or your environment allows you to be. If the environment is changing fast, you cannot really be bandwidth conscious. Right? Now, if you look at the IoT networking technologies, right, this is a nice picture which shows on the x-axis is the range of the communication technology, and on the y-axis is the bandwidth, right? So we see a lot of RFID devices. The range is very small, right? It's like within 1 to 2 meters kind of things, and the bit rate is also very low, like in kbps. But this works fine for RFID usage, like in shops and all, where RFID tags are used to monitor your somebody stealing things, or even for at the checkout counter to get the billing and all that. Right? On the other extreme is your cellular, right? Which has very high range in kilometers and very high bandwidth. But the other thing that is shown by the color coding is that the deeper blue means its cost is very high, right? Because cellular, you need an entire cellular infrastructure. So the cost of just installing that is huge. And so it's a very high cost solution, right? Wi-Fi is something that is very high bandwidth. I mean, again, it's similar to cellular, but its range is in tens of meters. And the cost is much less than cellular because you don't need base stations and stuff. Right? So this is also another parameter space that networks have to look at, right? Because now you just, depending on the use case, you have to pick and choose what kind of technology you are going to support. And the moment you pick a technology, you are kind of precluding yourself from competing in the market where the technology is something else, right? So for example, if somebody is making a device which is using cellular and you are making a device which is using, say, Bluetooth, then both of you cannot really compete in the same market, right? So the things like that, right? So this also has implication on the research part, because now you can design your protocols or your devices in such a way that you focus on the technology, in the networking technology, along with the applications. Right? Just to give an idea, like we are kind of now in 5G phase. So in 2020, we are in 5G phase. I mean, 2020, we have already started in 5G phase. Bandwidth is more than 1 gigabit per second. latency is less than 10 milliseconds, average speed is around 200, 400 megabits per second, right? I mean, we can get bandwidth greater than gigabit per second, but what we actually get is in the hundreds of megabits, which is a huge improvement over 4G, and obviously much more over 3G. But then we know even in India, 4G, even now 4G coverage is not pan-India. There are a lot of places where 4G still doesn't make financial sense to deploy. And 5G is still coming up. It's still in India, at least it's still in a very nascent and trial stage. So as I said, these technologies will have a huge impact on what kind of IoT devices you will be building in the future, and what kind and how do you have to optimize for the specific networking technology. And even with 5G, so each camera can use, for example, the cameras that I've shown in the worst case can use up to 10 Mbps bandwidth, right? A large installation can have hundreds of cameras. So we are already at 1 Gbps of bandwidth, right? Not an easy thing to solve if there are hundreds and thousands of cameras. You can again look at this documentation to get a better idea of which camera and what configuration is how much bandwidth and things like that. The other challenge is the resource constraint. Now, especially, I said this, right? Most of these cameras run their own machine learning models, right? Then the moment these cameras are capable enough of running machine learning models, which means they have GPUs and machine learning specific processors and stuff like that, like TPUs, people start using, I mean, people at least have the ambition of using these for more and more complicated models, right? Now, people who are familiar with machine learning models would know that models come at a price, in the sense that complicated models are bigger, right? We often hear about these NLP, natural language processing models coming out from Google or companies like that, where there are millions of parameters, right? So these models are huge. So most of these models would need a pretty large memory even to fit. These IoT devices do not really have that much resource, right? So we have to somehow tackle that challenge, right? So we have to work on tools and mechanisms to fit our models to the resources that are available. Right? Now, what are those techniques that are already out there? And of course, there's a lot of research that is going on in that. Right? So, for example, one technique is pruning models. Now, what do I mean by pruning models? A machine learning model or a neural network looks somewhat like this, which has a lot of nodes and a lot of edges. Right? Each edge has a particular weight. Right? Now, in a pruning mechanism, what happens is that weights which have like maybe very low edges which may have very low weights might not be contributing much to the model, right? So we can probably prune some of these edges. If you prune some of these edges, then your neural network, which is nothing but a DAG, right? It's a directed acyclic graph. So the graph becomes simpler, so which means the number of edges actually reduce, and so the representation of this graph becomes more compact, needing less resources to store as well as less resources during computation, because when you follow this path, you are going via say 3 of these. You have to do 3 computations here, whereas in this case you are doing 1, 2, 3, and 4. There are 4 computations being done here, right? Because now you pruned one edge away. So the computation also becomes faster. So this is one common technique used in pruning, in fitting models to more resource constrained environments. So it makes a dense network sparse, reducing the number of parameters and computation. So helps in storage as well as runtime computation. Okay. The next part is known as the quantization of models, right? Because here what happens is that instead of floating points, use integers to store weights, right? Specifically 8-bit integers. So that again, the floating point requires many more bits. You need 32 bits. Int 8 needs 8 bits to store the weights. So if you have large number of weights, if you are bringing it down to 8 bits, then you have a saving of like 1/4 You are using 1/4 the space to store the edge weights without having a considerable decrease in the accuracy or the performance of your models. Right? This simplifies the computation without noticeably impacting accuracy. Right? So this is a common technique that is used, and again, this reduces model size and makes inference faster. And finally, there is a technique called model optimization. Now, what does model optimization mean? It takes the original model and it converts it into an optimized version for specific hardware, right? So you might write your code in, say, TensorFlow or PyTorch or something like that, which are the common machine learning toolkits. And you can use tools. These tools are somewhat like a compiler, which will take your code and then kind of fit it or customize it to the specific hardware that you're going to use, right? And there are optimization tools for all of these, like for example, Apache, TVM, AWS, SageMaker, Neo, things like that. These are tools that are publicly available, and I'm pretty sure there are proprietary tools with companies like NVIDIA and Google who use that to do their own customization. So that is known as model optimization. So you have a big enough model or a generic model, and then use these compiler kind of tools to customize it for the specific device that you have. So these are the three techniques for model optimization. Now I'm going to go towards the last part of the presentation, in which I'll handle the last challenge. And this is a challenge. This is the area of machine learning operations. Right? This is a challenge which, in a strict sense, is not a research challenge. It is mostly an engineering challenge, but as is often the case, a lot of engineering challenges lead to nice research problems. Right? So what is the field of ML operations, right? Usually what we see is that there are machine learning engineers who are very adept in writing machine learning models. And these days, for example, if you want to do a competition within your university about some machine learning models, say identify traffic lights or something like that, anything that you can think of. I'm pretty sure students can come up with a working model within like a couple days to a week, and they can work on it and optimize it and things and make really good models, giving very high accuracy within a week, a month, or whatever, like definitely within a semester. Right? But what is very difficult to do is to take such a model and actually productionize it, right? Actually run it in production. And these are the challenges that come under the scope of machine learning operations. So what is machine learning operation? It is the processes and collaboration between three different groups of people: the data scientists, which is basically machine learning engineers; the systems, which is the infrastructure on which your code will at the end run, or your entire system will at the end run. And these systems can be gigantic cloud-based systems, or it can be your laptop, which is a single small system, right? And the operations engineer, which are basically engineers who are managing the infrastructure. So if it's a cloud-based system, there are engineers who manage that infrastructure. So this is an intersection of those three systems. So it is the process and the collaboration between data scientists, systems, and operation engineers to manage the life cycle of machine learning within an organization. That is kind of the formal definition of machine learning operations. You will see the jargon being used in ML ops in a lot of places. I'll just set myself another timer. So machine learning operations, you will see the jargon ML ops being used in a lot of articles and when people talk about this. So again, just to make it a little bit more clearer, when we think about machine learning, the perception is this, that the machine learning code is this big elephant in the room. And there are a lot of peripheral pieces which are important, like data verification, data collection, machine resource management, the serving infrastructure, monitoring infrastructure, all these kind of things. People know that these are important, but the perception is that the machine learning code is the biggest and fattest piece, and that needs our most attention, whereas the peripheral things are important, but it will get done, right? However, the reality is very, very different, because for most machine learning use cases, including use cases in industry, the machine learning part of it is very, very small. And in most cases, very few companies or very few people actually develop a model from scratch. You would simply take a model that works, you know that it exists from the open source, take it, tune and optimize it for your use case, and get it working, right? That is usually a considerably simpler exercise than these peripheral things that people consider to be on the periphery, but actually are big pain points when you want to make an engineered system for production use cases, right? Simple issues like data collection is such a big pain point that most companies, the reason that your machine learning models usually don't work well is because you do not have good data or large enough data sets which are well annotated, right? Just collecting data doesn't help machine learning, because once you collect data, you can collect tons and tons of data, but you would also need to spend a lot of resource and time in annotating the data so that you can use the data to train your models. Data which is not annotated is at this point in the machine learning journey is useless. There is a lot of research being done in self annotations and semi supervised learning or unsupervised learning and things like that, but those are still not mainstream, and even the research is still quite some distance away. So next is, this is the reality, right? The elephant in the room is actually very small piece. Everything else becomes pretty big. Just as an example, serving infrastructure, right? Once you have a model that you are satisfied with, right, now you want to use it. So that serving infrastructure has to scale with the number of use cases and things like that. That is not something that a machine learning engineer would know very well how to do. It would be the domain of the systems engineer or the site reliability engineer, right, who manage large infrastructure. So for that piece, I would like to introduce an open source system that we in Meraki also use to develop our machine learning operations, and this is known as the project is known as Kubeflow. It's a machine learning toolkit for Kubernetes. Right? Now, what is Kubeflow? Again, this is verbatim from their website. Kubeflow is an open source project dedicated to making deployments of machine learning workflows on Kubernetes simple, portable, and scalable. Right? So here there is something which is very important. Even in the definition, it says on Kubernetes. So which means that Kubeflow assumes that the underlying system for managing a large infrastructure is Kubernetes. It will not work on a regular operating system. It will not work on any random other layer below it, right? It needs a Kubernetes endpoint, which is a containerized management system, a container management system. So the overall picture kind of looks like this. At the very end, you have your infrastructure, which can be your laptop, it can be your cloud-based infrastructure, or it can be your own servers. On top of it, you have your container runtimes, like your Dockers and stuff like that, or container D. And on top of it runs your Kubernetes, which is your container management system. So you can think of it as an operating system for underlying containers. So it manages spawning containers. If containers go bad, it respawns containers, killing containers, adding new devices into the infrastructure pool, all those kind of things, right? On top of that is what is where Kubeflow is running, right? And Kubeflow is then used to actually manage your entire machine learning lifecycle, which includes training your models, rolling out your models, serving your models, a lot of basically whatever pieces I showed here. Most of these pieces are there in Kubeflow. Not all of them are there. It's a relatively new project, so not all of them are there. But other than that, there are. It does have a lot of this. Right? So this is how it looks architecturally from a layering point of view. Now, what are the major components on Kubeflow. As I said, there are a lot of pieces in Kubeflow, but the major components that we use are something known as Jupyter Notebook, which allows the machine learning engineer to, it's an integrated development environment. It's a browser-based IDE, and it supports multiple ML frameworks. You can code in PyTorch, you can code in TensorFlow, you can code in Scikit, anything that you want. Most of these work here. And if something doesn't work, you can easily write a plugin for it. So Jupyter Notebooks are used by machine learning engineers to quickly code up sample use cases or proof of concept use cases, and that allows you to and then convert it into containers and deploy in large scale systems and stuff like that. And then there is the concept of Kubeflow pipelines, which is nothing but an intuitive graphical machine learning workflow, because a large enough workflow has several pieces, as opposed to a proof of concept where you can write one module and get done with it. But just like any realistic software has many modules, a realistic machine learning workflow also has many modules. And this allows a graphical workflow model. I'll show pictorial representation of how these look like. And it also, Kubeflow also supports advanced machine learning tools such as neural architecture search, auto machine learning, and hyperparameter tuning. These are all ways of coming up with, excuse me. These are all tools for coming up with, automatically coming up with the best machine learning model or best neural network architecture. Right? So these are, again, these are high-end tools. Not everybody needs to use them, but this open source code supports it, and we use it actively within our group. So just to give an example, this is an example of a Kubeflow notebook. It's GPU enabled. The GPU enabled is more like a marketing gimmick, because if the Kubernetes platform has GPUs, then this automatically can use GPUs, and it can run Scikit, TensorFlow. I don't see a PyTorch, but yeah, it comes with all these capabilities or plugins. The pipelines is, as I said, it's a modular representation of your workflow. So for example, you can have data fetch and pre-processing as a module. You can actually have the model training. You can add in maybe a hyperparameter tuning, a hyperparameter tuning block before the actual model training, and then finally model validation, acceptance, all these. It allows you to do it in a graphical manner. So you have different blocks, you just link them up, and that's how your workflow will work. And as I said, there is hyperparameter tuning. I'm not going to go into the details of it. People who are aware of hyperparameter tuning know what it is. It is basically a way to tune parameters of models that cannot be learned during training. So once you start the training process, things like learning rate or momentum, these are fixed values. These cannot be changed during the training process. But then different learning rates can lead to different accuracy of the final model. Different momentum can lead to different accuracies of the final model. So those, you need to play around with those numbers. So that is known as hyperparameter tuning. Hyperparameters are parameters which are outside the model, or you can think of them as arguments to the model. So they have to be fixed, arguments to the training process. So they have to be fixed before the training process starts. And in order to fix it, you have to be able to, in order to make a correct or intelligent guess about that parameter value, you need some sort of strategy. That is what hyperparameter tuning allows you to do. I'm not going to go over this diagram. Again, this will be there in the slides that I share. So this is specifically for Kubeflow's hyperparameter tuning, but the idea is generally true for all hyperparameter tuning systems. And this can, as I said, hyperparameters can greatly impact the performance of models. So this is my last slide. After that, I'll take questions. So the takeaways are that surveillance cameras have come a long way. IoT itself has come a long way. We had the traditional IoT, now we no longer have that. And the edge is no longer dumb and has the capacity to take decisions on its own. Right? High bandwidth usage and resource constraints are major challenges. So these are likely to be challenges both in implementation as well as in research for the foreseeable future. And ML operations is a crucial skill in real world products. So as the last part of my talk presented, ML operations or ML ops is very, very crucial for making anything run at production grade or at scale, right? Again, it's not necessarily a problem of particular interest to academics, but then these days academics and for a lot of systems related issues, the difference between academics and practitioners is blurring. So even academics have to work with realistic systems. With that, I end my talk and we can take up any questions.
Thank you very much, Dr. Amit. It was a very informative talk. So we have a question from one of the attendees here.
Yes.
The question is, sir, is your company offering any paid research internships for PhD scholars in the field of machine learning or deep learning? If so,
yeah,
what is the selection process? Yeah.
So Cisco does provide certain internships. The way it does is all of Cisco's hiring, including intern hiring, happens via two channels. One is if Cisco directly goes to the university and they do hiring and all, but then during this pandemic, that has reduced a lot for the last 2 years. I don't think we have been actually visiting campuses. The other is there is a portal called jobs.cisco.com. So if you just search for Cisco jobs, I think that should come up in Google. There is criteria for internships and stuff like that. Right? Having said that, most of the internships, at least in India, usually take bachelors as well as maybe some master students. There are very, very few PhD interns, at least in Cisco Bangalore. I know there have been PhD interns in Cisco San Jose, but then that's not really open for people from India because of visa issues and all those things. I know there are students from IISc who kind of work with some people from Cisco Bangalore, but that's because of a specific collaboration that Cisco Bangalore has with IISc, both being in the same city. I think that's an easier path. So yeah, so that's my suggestion. You can look at jobs.cisco.com. That's probably where you will find most of the internships. The other way is to, if you know people, you can approach them and see if they, but my understanding is that PhD research internships are very rare, at least in Cisco Bangalore.
Okay, thank you, Dr. Amit. And I have one more question from my end. Actually, you mentioned about the resource constraints at the last slide, right? So is bandwidth is the only constraint you are feeling, or like there will be any other constraint?
No, so two constraints, right? Primarily that I hinted about. One is bandwidth, and the other is the device itself is very resource constrained. These are small devices. Camera is actually a very large IoT device, but there are a lot of other devices like which are primarily sensor-based devices and all. The amount of memory and CPU that you get inside of those is very limited. Right?
Okay.
So you cannot simply start running very complicated models because you just won't have the first, you won't have the memory to fit in the large models, and even if you could fit in, you wouldn't have enough CPU resources to be able to actually run it at a decent enough frame rate or whatever. Right?
Okay.
You won't be able to do.
So just another sub question to that, like, will there be any constraint on energy or power?
Yes, there are huge constraints on energy and power depending on the use case. For example, I was showing the case of these surveillance cameras, right? So usually these are powered. These are not battery operated. So as long as these are powered, then people tend to not think too much about power consumption as long as they are within certain limits, which are like government limits and things like that, right? But for example, even in our group, we are working on much lighter weight cameras, which can basically run on batteries, right? Now, the moment you bring in batteries, the issues of duty cycle, which is how long you want to keep it up versus how long you want to keep it asleep, becomes very important. For example, in a camera, you could every time you are seeing a scene, you are using energy, right? Now, a camera could be paired with a proximity sensor or a door open sensor or something like that, so that the camera usually doesn't see anything and it's practically using close to zero power. And when the sensor says, oh, hey, there is a door open trigger, that's when it sends the trigger to the camera, and the camera then starts recording or starts seeing at least, right? So that way, that's basically intelligent management of the duty cycle. Instead of having a fixed frequency when you wake up and when you sleep, these are intelligent triggering of a duty cycle. So those are also becoming. I mean, you will find devices like that, but in general, for camera kind of devices, power is still not a major concern. For other kind of sensors, for example, Meraki also makes other sensors like humidity sensor, temperature sensor, and all. Again, those are meant for a lab environment, specifically for Meraki's products. So again, they are powered by like PoE. Even our cameras are powered by PoE, so power over Ethernet. So inside a lab, you don't expect things to be running without power, right? But there are sensors which will run on batteries for like multiple years using technology, like using communication technology like BLE, Bluetooth Low Energy and stuff like that. Right? So yeah, in the general space of sensors, power consumption is a big concern. But specifically for what Cisco Meraki is building and what we are working on, it is still not really a concern because we are not targeting that market yet.
Thanks for your detailed answer, Dr.
Amit.
Yeah.
Yes.
Yeah, Dr. Amit, it was a very nice talk. Yeah, I have a couple of questions actually,
Sure.
because I'm also in the field of computer vision. Actually, my work basically in the, as you said correctly, academicians, we actually work only on the algorithmic side. We are not at all worried about the deployment part. And as you said correctly, that is the major, right? Which we are very much aware of. Actually. But I have my first question is, you talked about things like how to make a neural network maybe edge friendly by maybe pruning, optimization, and things like that. But I would like to know in the camera, the surveillance, intelligent surveillance camera that you make. So if you look at an algorithmic side, what the type of work that we are doing is, anomaly detection, number plate detection, or accident detection, and then a lot of sort of interpretation that we do. And what are the specific intelligent works that your camera does?
So for us, most of the time, what we do is our target market is enterprises. Right? So most of the time, we are not selling into households because these cameras are reasonably expensive. This is not something that you would buy for monitoring inside your home. There are much cheaper solutions for that. Right? So for us, our primary target are enterprises, so offices, industries, factories, things like that. So if you place these things in offices, right, there are multiple things that people use them for. For example, one common thing is workspace occupancy, right? So how many people are there in the office? Even before the pandemic, people were interested in that because that allows you to kind of consolidate your workspace and stuff like that. How many people are visiting at what time of the day? Then there are use cases such as automatic, what should I say, like, so the video that I couldn't show, it shows that you can take a look later. So there is a person who comes, say your employee comes to your office, right? And the camera is seeing the person. The employee comes in a bike. So the employee has a
helmet,
right? So this automatically understands that the person is wearing a helmet or the face is not visible, right? So that means that immediately we can't do a detection on the face and identify whether the person is an employee or not. So there will be a message displayed on a screen saying that, hey, please remove your helmet, right? And the person removes the helmet, swipes in the badge, and we can do everything in the background. And then the door automatically opens, right? Those kind of use cases are there. Though facial detection is something that Meraki as a policy doesn't do because that leads to a lot of privacy issues. Tomorrow somebody might say, hey, why my why am I being identified and things. So there are a lot of privacy issues. India is kind of catching up on the privacy issues, but in the Western world, it's a big thing that your identity should not be revealed in any way and things like that. So as a policy, we don't provide any face detection model pre-packaged in the camera. But the stream from the camera, the video stream from the camera is available to anybody who purchases our cameras, and they can then do their own modeling on top of it and do facial detection. We cannot prevent that because that is up to their usage. So this is one type of use case. Then there are use cases of, as I said, motion heat maps. So for example, staircases or entrances and all, right? Like, what is the density of people moving through it? Right? For example, if there was a fire alarm and we suddenly see a large number of people moving through it, that gives you an idea. The heat map, if it is like really red, you know that, like, say 200 people went through that in a very short time span, right? Now that might lead to a better design of your exits and stuff like that, right? So motion heat map is a big use case. We are working with so a lot of the use cases are worked with our customers after they tell us, hey, we really want this to be done. Like, for example, restaurants, right? They want to be able to figure out that, okay, somebody ordered a coffee and he ordered the coffee at 10:50 a.m. And since the order has been placed, they track the coffee cup, because the coffee cup goes first to one person, that person fills up milk, somebody else fills up coffee, and then somebody else puts the lid and things like that, right? So they track that specific coffee cup all throughout and see that it gets out in what time. That leads them, that allows them to understand if their workflow, if their physical workflow is efficient enough or not.
Yeah, I understand.
Right? So
yeah,
all
that's
those
clear.
kinds of use cases are there.
Yeah. And again, another question that I have is, Dr. Amit, so your edge computing means basically, will you be deploying some trained model for some particular application? Is it always
Yes.
Deploying some trained model?
Yes. For us, these are all trained models. We do our own training for these models that come pre-packaged into the camera. As I mentioned, we recently, like 2 months back, I think in March, we launched a software feature which allows, suppose you buy your camera, it will allow you to train models and then install it on our camera. So you are not limited by the pre-packaged models. You can install whatever models you specifically want, subject to some limitations like size limitations and stuff like that.
Okay. Yeah, thank you. I have another important question, which you mentioned clearly that, the academic community is concerned very much into the algorithms and the AI parts. And again, if you look at, vision conferences, the top vision conference like CVPR, ICCV, ECCV, and all, they are into algorithms.
Yes.
Even though, CVPR actually conducts some workshops like embedded vision, etc. Otherwise, they are very much into algorithms. And also, if you, again, ML conferences, if you look at the neuro IPS and all, so they are also into algorithms actually. But you clearly said that, this is not the magic part. When you look into for deployment, when you look about deployment, this is a very, very minor component.
Yeah.
So now my question is, why the academic community is again spending their time only on the algorithm part? Or I think, or maybe the other deployment part, maybe the duty of maybe the other engineers, right?
Yeah.
May not be the vision engineers, right?
No, so there are, see, I mean, there is nothing wrong in what's happening. This is not a situation that is expected to change, and there is nothing wrong in that. See, academics usually are, at least in general as a community, are 10 to 20 years ahead of industry, because you're working on algorithms which will, for a lot of things, the applications are not even ready yet, right? The industry doesn't know what to do with it, right? A lot of very high-end algorithms, all the algorithms that we use kind of came from academia, almost in everything, right? Because somebody started working on it and it took them 10, 20 years to perfect it, and only then it would make sense to bring it to industry, right? Now, for example, companies like Google and these hyperscaler companies, they actually publish a lot in your NeurIPS and your CVPR and all those things, because they have a very nice juxtaposition of algorithmic things which help with large scale deployments and stuff like that, right? A lot of things in academia these days in the systems area as well as ML area, the problem happens is that like the data sets that is available to a hyperscaler, unless you as an academician collaborate with them, you will never have access to them. Yes. I mean, your university, even if you monitor everybody, is like 10,000 students. But if Google in a single day is getting data from a billion people, right? So it's just not comparable. So that's why you will see a lot more academicians are collaborating with these companies and going on like sabbaticals and stuff like that, and getting their students to work there so that they can collaborate more and get access to the data. Now, having said that, as I said, there is nothing wrong in what's happening. Academicians will work on algorithms, which 10 years down the line will get started using. Like, for example, all the object detection models and all are now being used in camera, but they had been developed like 5-10 years back. So it will, I think that is a healthy way of doing things. It is going to continue. But this collaboration is becoming more and more important because even the algorithms are now based on, I mean, you can make better algorithms if your data set becomes larger, and the data set is not usually available to academics that easily.
Yeah. Dr. Amit, my last question is, having said this, in our Saram University, in our electronics department and in our computer science department, there are many faculty actually working on this computer vision algorithms actually. So if is there any possibility for any collaboration with Cisco? So maybe, and if at all it is there, what should be the domain of collaboration?
So yeah, so this is always a question, and I, frankly speaking, I don't really have a good answer to it, because the problem with any company, including Cisco, is that when there is always a lot of these IP related issues when you collaborate with companies, right? So suppose tomorrow you come up with a wonderful algorithm while you were working with some Cisco engineer, right? Now Cisco would want to get access to that IP, right? Exactly, and even though in most cases academics are okay with the IP as long as they are able to publish the work and all, it is not a very healthy relationship, because
that is correct. Yeah.
It is the core of the relationship is a little bit of distrust. Hey, my IP is being stolen and things like that. So I don't really have a good answer to it. There is one approach though, which is most companies have, like even Cisco has something called a Cisco Research Center, where there are these requests for proposals that are there, and academics from all over the world apply to this and get funded, right? Okay. The good thing about this funding is that it is a pure and simple fund. It is a research grant. Cisco has no claim over the IP or whatever you do. Cisco has no say in what you do with that money, obviously in good faith, right? We expect that you do what you have asked, what you have claimed to do with it.
So that is done after a global call, right? Global call, or maybe it is.
Yeah, it is a global call. It is not usually done country specific, but there are several Indian universities as well who are funded. The bad thing, that's the good thing about it, is that this mechanism exists. The bad thing about it is that usually companies show these expenses as research gifts, right? And so from a tax point of view, companies get tax benefits.
Okay.
The moment, and in India, it's like CSR benefits, right? The moment you get CSR tax benefits, then Cisco is legally not allowed to actually gain anything from it. So for example, if I work with you and forget about patents and things like that, some nice publication comes up, and since I have worked on it with you, both of us would like to be co-authors in the publication, but that is not allowed, because that means I, as a Cisco employee, am getting a benefit out of it. I'm getting a publication. Right? So this mechanism is good for the academics in a sense, but it is still not good for collaboration, because it really doesn't allow the collaboration. So not a very good answer that I can give you. There are several universities which has approached Cisco and other companies, I'm pretty sure, with which they work, but I haven't really found especially in Bangalore, I mean, Cisco India, I haven't really found a very good working model, so to say.
Yeah. Okay, thank you. Thank you very much.
Dr. Abid, there is a question from one participant. I just let me read it out. Can you please touch model monitoring part and best practices?
Model monitoring itself is a big area. I should give a disclaimer that I personally do not work in model monitoring, so I might have a little bit outdated and not so correct information. But in general, what happens with model monitoring is that in machine learning, what generally happens is that you have a data set, and the data set allows you to train a model, and you get that model and you start running that model in, say, production or whatever, right? Now, what happens is there is this concept of drift, which means that the data itself can start changing a little bit. So, for example, what you trained on, say, 6 months back is no longer relevant, right? Or it is relevant, but only partially relevant, and the new data is little different. So you will have to monitor your model for accuracies and misses and things like that, and then figure out, hey, my model is actually, its accuracy is getting lower and lower. So I need to start retraining the model, right? So that is one part of model monitoring. Then there are also other monitoring aspects of model as to like its own resource utilization and stuff like that. How much is the inference taking? How much CPU resources is the inference taking? What is are we facing any scalability issues in when running the model, things like that, right? So these are all model monitoring issues. And there are, what I should say is, like, best practices are, again, it depends a lot on the industry and a lot on the specific models. So any model is only as good as the data that you have. And you start with a model, you have excellent model, but as I said, the data itself will change, your environment might change, and so it will be very difficult. I mean, it will be very difficult for the model to keep up the same accuracy. So you have to constantly keep monitoring the model, retraining the model, and pushing the updated model into production. Again, when you push an updated model into production, there are different issues. For example, the basic concept of A/B testing, right? So for example, if Google is doing some sort of when you type on Google the query, it does a query completion, right? Maybe it changed something in the query completion. It doesn't install the new model for everybody, right? It just does maybe for 1% of users, and then kind of validates it and tests it and monitors it and say whether the performance is okay or not. And then slowly it goes up and up, and finally at some stage it goes and replaces it for everybody. So that's generally the case with model monitoring, but it's a vast area. I do not really work in that area, at least as of now.
Okay. There is a follow-up question on that. How Meraki handles after shipping products, that is model monitoring.
Okay, so that is model monitoring, as well as how do you get data from customers. So there are two usual ways. Usually what happens is that once a camera is running up at some location, we don't have access to their data, right? I mean, that's because for privacy issues and all, we don't have access to the data. So if there are issues in the model, right? Suppose the model is supposed to count the number of peoples and it is overcounting by a large number, right? Then they basically report it as a bug, and then we have to look at it, right? At that time, we might ask for their actual clips. We will take those clips, run our models internally, and see why we are going wrong and things like that, right? That's the usual practice. We don't automatically or continuously monitor models on cameras that we have shipped, because we no longer own the camera, right? The camera is owned by the customer. Recently, we have started a project in which we are, with the customer's permission, that is, the customer has to sign up by accepting a condition. We collect data from the customers and keep it in our pool so that we can train our models better, right? Because the problem, as I said, your models are only as good as your data. The problem with training models is that unless you have large set of data from a diverse background, diverse source, it's difficult to come up with highly accurate models. So we are collecting models we are collecting data from a lot of our customers so that we have a very diverse pool of data, and that will help us improve our models.
Thank you. And one more question from our panelists. What our BTech students shall prepare to be industry ready, especially in this computer vision and edge AI?
So this good question, and I think it's very relevant. I mean, it has always been relevant. So the one thing is these days, due to YouTube and all those kind of things, there are a lot of nice courses or kind of channels which are into this, right? So I think all students, and including faculty and people who are in this field, should browse them and see what is interesting, what do they find interesting, what are people doing, right? Then, for example, Google has TensorFlow summits. There are a lot of summits, and most of the summits, after the summits, even though the summits themselves are paid, all the videos and all are made public on YouTube. Right? So those are very good sources of information to learn about these toolkits, technologies. Many, especially because of the pandemic and since the pandemic, a lot of events happen in hybrid format. So and the online registrations are really cheap and you don't need to travel. So attending those, again, don't get overwhelmed in attending those because you don't want to attend everything, but a few, 1 or 2 good events in a year that will, at least if you don't end up learning about those, you will at least end up knowing about, okay, this is how things are being done. Because if in a TensorFlow summit, what they're going to talk about is going to be something which is very current instead of a place where things which are being told might not be very current, right? So it's good to go to these places or attend these, or at least on YouTube, go and watch these videos and all to get an understanding what is being used currently. Additionally, I would say, I mean, it should be, at least in engineering, it should be mandatory that people go for industrial internships because that's at least you will, again, not all the projects are going to be interesting. Not everybody is going to have a very successful internship or a very happy internship, but at least you'll get to know, okay, if you come to Cisco or if you come to Google or if you come to Amazon, you will know, okay, these are the technologies that they're working on. These are the day-to-day tools that they use. This is how things get done. So I think a lot of industry readiness is knowing how industry does the work, not necessarily exactly the technology. Because I can give you my example. When I joined industry after my PhD, in every meeting, I used to go down and just the terms that were being used, I used to just note it down because none of the terms I could understand. What are the terms they're using? Because there's a lot of jargon being used in industry, right? And then when I go back and look at the jargon, what it means, then you understand, okay, you have read about something in your courses and books which resemble these things. So that means it is something like that, right? So that for a lot of students becomes very difficult because you just hear so many terms and you get lost in the terms instead of actually focusing on the real thing. But if you do industry internship, then you get into that practice during your bachelor's itself. And so then the transition to industry becomes very smooth. Again, obviously not everybody is going to transition to industry. Some will obviously go to research and academia. So for them, the experience would be different, but I would still recommend them to go through internships because you really do not know as a bachelor where you will end up in.
Yeah, that is very much fine, Dr. Amit. But I again suggest that so when we teach courses like this, the very specific elective courses like this, and I think we should invite people like you maybe for that particular class. But, if you're arranging a talk like that, nobody, maybe 1 or 2 people will attend actually. For if I am teaching a computer vision course for a particular batch, and then for maybe at least for 2-3 lectures, I should invite people like you.
Yes, that is definitely true. Yeah, good
that
point.
Is one of the best things.
The Yeah, that needs a little bit of initiative from the faculty side, because you need to go and actively invite, and then oftentimes,
so that the entire class will get an idea, and then if some people are then interested, then if some students are then interested, then they can go further.
Yes.
Thank you.
Final question from my side. What is the hardware platform you can suggest for computer vision with edge? There is lot available in the market, like Oak D cameras, that is Open CV AI depth cameras, I believe. So what is your suggestions on
this?
that?
I actually don't know the answer to, because I personally have not looked at other things available that are freely available. I mean, we have our Meraki platform itself, which is basically some version of Linux, which is running on the platform, right? I don't really know an answer to that. Like, what is freely available outside? Obviously, OpenCV and all are there, but that's not really, that's still a software platform. I don't know if you can get anything hardware wise that you can start working. You can always make stuff with Raspberry Pi. That is always an option. So you can always build something with Raspberry Pi, and a lot of people do experiments on that. And if you want to do IoT specific, then as I said, the ARM based boards, those are also available. And so, and a lot of software around those boards are freely available from ARM. So you can use that as well.
Okay, thank you. Thank you.
Hello, sir.
Hi, Indranil.
Actually, I have just one question.
Sure.
That is, you said that actually in your camera, are you using actually the processor? That means what the processor you are using? Is it actually that customly made by the Cisco, or it is any ARM processor you use? And then
so the camera has the current camera has two processors, in the sense one is just for like a regular CPU, which runs the operating system and a lot of other. The camera runs a lot of other services other than this machine learning stuff and all. But then there is specific third-party chipset which is used for these machine learning workloads. And these chipsets are like Qualcomm chipsets and all, which are used in your mobile phones and all.
yes.
So we don't build. Cisco builds ASICs for routing. We don't build chips for these kind of applications, at least not yet.
Okay. No, actually, as you are saying that in future you are going to provide the battery operated camera.
Yeah, but again, this is not going to be a chip that we'll design. It is going to be what will I say? I mean, we'll probably design the board with components from outside.
Okay, so that means all these components will be actually that nanowatt power actually consumption sources. Exactly. You will components you will use, and they will make.
Yeah, so more than, see, the components by themselves. I mean, no component uses any power if it is not being used. So it is more of a the challenge is more in having this duty cycle management and all, which will allow you to have a very low power use. And obviously, newer components, low power components, all are there. But the bigger challenge is to make it more. What should I say? Make it more intelligent in using its energy. Yeah, because chip building is not easy. Just to keep it simple.
Yeah, actually, I
mean, designing a chip is, we have the capability of designing chips, but productionizing a chip is a long process.
Yeah, no, actually, I have seen that. Let's say, like Apple's nowadays, they are making their own processor on their particular product. So Cisco, I know that they make hardware products.
Yeah,
like
no, Cisco. I mean, the reason companies like Cisco, Juniper, and all those kind of came into prominence is that they built, because of the hardware, they built chips, and those chips were able to give a lot of bandwidth and features. But even for that now, companies like Broadcom and all, for commodity chips, it's much easier for to kind of buy those and install them, because they are just making chips, whereas Cisco is also building a lot of software and a lot of other things.
Like plug in and then use this. So that means I think nobody other has any questions. Is there any questions from the other participants?
I don't see anything else in the chat anymore.
Okay. Then actually, I would like to thank you for accepting the invitation on behalf of SRMIP. And it was a very actually enormous and in-depth knowledge which you have shared among us. And I hope that it motivates our student and all the faculty members who joined, and later on also who will actually see these things in YouTube. They will be much more motivated to do research in this particular direction, which is this, I think, the recent trends or the future trends. So, and I would like to thank all the panel members and all the audiences who has attended this particular event. Okay, so and thank you again, and I hope I will connect with you later. I'll talk to you in through the evening.
Sure. Thank you, everyone, and this was a great honor, and thanks for inviting me. Hope this turned out